So I'd like to begin by thanking the organizers for the opportunity and to everyone for attending. So the title of my talk is One and Two-Neutron Halos in Effective Field Theory. My name is Bijaya Ancharya. I'm a graduate student at Ohio University, and this is work I did in collaboration with my dissertation advisor, Daniel Phillips, Genji, now at Triumph. Philip Hagen got his PhD from Bonn recently, and Hans Sonderhammer at Bonn and Darmstadt. So here's the outline of my talk. I'll begin with a brief overview of neutron halos and try to motivate why it is a good thing to study them. And then I'll discuss some early experimental results that are relevant to my work. And then I'll move on to a brief summary of effective field theory applied to one-neutron halos and discuss how we use this to analyze experimental data on carbon-19. And then I'll move on to effective field theory for two-neutron halos and discuss applications to carbon-22. So here's the chart of nuclei, proton number versus neutron number. Stable isotopes are shown in black. Proton-rich nuclei lie in the region above the line of stability. Neutron-rich nuclei on this side, and some nuclei close to the drip line have a halo structure. What that means is that the wave function of a nucleon or the wave function of a few nucleons extends to distances much larger than the wave function for the rest of the nucleons that are tightly bound, forming a core. So these are some properties of halo nuclei. They have a low separation energy for one or more neutrons. Now I'm focusing on neutron halos from now on for the rest of my talk. So low separation energy for one neutron or a few neutrons. The rest of the neutrons and protons are tightly bound into a core. These nuclei have large cross-section for transfer and breakup reactions involving the halo neutrons. And they have a large matter radius. Now, since these halo neutrons, they cause a shift between the center of charge and the center of mass, they have enhanced charge radii and dipole moments. You can think of it as motion of the core around the center of mass of the nucleus. So that's why it's interesting to look at electric properties of this nuclei.
Can you say a bit more specifically what you mean by low separation energy?
It takes low energy to separate a neutron from the nucleus.
Okay, so it's sort of weakly bound.
Yeah,
That's
weakly
what you
bound.
mean by
Yeah,
that.
right. So this is the technically correct word for the energy it takes to separate a neutron from a nucleus. I like to call it binding energy because we look at it as two-body and three-body systems. But nuclear physicists don't like this term binding energy because when they say binding energy, they want to separate all protons and neutrons. So it's, yeah, they want us to say separation energy.
I am happy with that. I just want to make sure I know what.
Okay. Okay.
Low neutrons means, and basically it's like Coulomb
Okay.
in terms of being small compared to excitation energy of the core. Or
Small compared to the separation energy for the rest of the protons and neutrons. 7 or 8 MeV per nucleon it works pretty well for nuclei in most mass region. It's a little lower on for lighter nuclei, but anything that's say 1 MeV or less, that would qualify as low.
it's just okay.
You have a valid point. So
Yeah.
if the excitation energy of the core is very low, then you have to make your theory more complicated and include this additional excited states.
Yeah.
So in the ideal framework, you would also have a very high excitation energy. If you only have a few states with low excitation energy, you can include them. But if you have very many, then it won't get you anywhere.
So here's why it's important to study this nuclei. First, nuclear reactions. Some of these nuclei participate in nuclear reactions of astrophysical significance. Take neutron capture reactions, for example. Understanding how neutron capture happens in this highly neutron-rich region of the nuclear chart is important for understanding our process nucleosynthesis, which is important to describe the relative abundance of the heavy elements in our universe. Nuclear structure. Traditionally, nuclear structure studies have focused in the region close to the line of stability because it has been very hard to produce these exotic isotopes. But recently, over the last 2 decades, we have managed to overcome the technological challenges associated with producing these beams. So this is a relatively young field. So this is the relatively unexplored region of the nuclear landscape. So it's essential to study this nuclei to complete our understanding of nuclear structure. Next, universality. Studying systems like this will help us connect to other systems which look very different, like systems of eunucleons and cold atoms near a Feshbach resonance. But what these things have in common is large scattering length compared to the range of the interactions. So it's interesting to look at properties that are common between all these fields. One example would be to look for the possibility of finding Efimov states in this 3-body system. Now I'll move on to some early experiments that will be relevant to my talk later. So that is RMS matter radius of nuclei in the helium, lithium, and beryllium isotopic chain. And that's the famous A to the 1/3 line, which works very well for heavy nuclei. So you can identify these nuclei that have very large RMS matter radii: helium-6, helium-8, lithium-11, beryllium-11, and beryllium-14. All of these are known halo nuclei. So in this case, Glauber model calculations was used to deduce the matter radius from reaction cross-section measurements. What is actually measured in the experiment, and this data comes from measurements from all over the world, different lab facilities. So what is actually measured in the experiments is the reaction cross-section, which depends on what target you are hitting this nuclei with, what energy you are scattering at. So you need a reaction theory to isolate the structure from everything else that is going on. And that is non-trivial for matter radius measurements. I'll come back to that. For the moment, here's a different class of experiments. These are neutron removal studies. So what happens in these experiments is that you have the halo nucleus, carbon-19 in this case, it's a 1-neutron halo, incident on a target. It could be a high Z target like tantalum in this MSU experiment, or it could be a low Z target like hydrogen. So when this halo nucleus is incident on a target, the halo neutron is removed, and the outgoing carbon-18 fragment in this case is detected, and its momentum is measured. You could measure the longitudinal momentum parallel to the beam axis, or you could measure the transverse momentum. And that's the momentum distribution. This kind of experiment, it's been widely used to identify which nuclei have a halo structure. First, because if you look at the integrated cross-section, the area under the curve, it's very large for halo nuclei. Second, the sharpness of the peak. Now, if you ignore final state interactions and certain other things, the momentum distribution of the fragments after the breakup reflects the momentum distribution in the bound state before breakup. That's in the sudden approximation. So since this halo nuclei, they have a wave function that extends to large distance in space, in momentum space, the wave functions are sharply peaked. And that's why you see sharp peak in the momentum distribution of the fragments. So here's... That's an MeV, sorry. So the paper I clipped this from didn't even have that. I forgot, I remember to put that in, but I forgot to put the units, sorry. Yeah, so here's a different class of experiments, Coulomb dissociation experiments, and I'm going to focus on them a little bit. So that's the Coulomb dissociation cross-section plotted versus the relative energy of the fragments after the breakup. So in this experiment, the halo nucleus, carbon-19 is incident on a highly charged target, lead, and it fragments into carbon-18 and a neutron. In principle, there is this nuclear contribution to this breakup. It's not purely Coulomb. That's actually the difference between the diamonds and the circles. That contains nuclear contribution to this breakup process, and that's just purely Coulomb. It has the nuclear contribution subtracted. And I'll tell you in a moment how they do that. But first, it's this dotted line. It's calculated using Woods-Saxon potential between the core and the neutron at a separation energy of 530 kiloelectron volts. So it turns out that this width is sensitive to this neutron separation energy. So these reactions, they are useful in determining the neutron separation energy of the halo nucleus. So I'll say a few more words about Coulomb dissociation reactions because that's what I'm going to focus on for the rest of my talk. So here's a simple cartoon of what happens. You have this carbon-19 incident on lead-208, a highly charged target. And that's the trajectory in the semi-classical approximation. That's the traditional, the well-known Rutherford trajectory. Now, if you demand that you are only going to look at breakups that happen only a certain impact parameter outwards, if you put a cut in the impact parameter like they did here, greater than 30 Fermis, you are essentially outside the range of the nuclear interaction. That's because if you add the sum of the if you add the radii of these two nuclei, you get a value around 12 Fermis. Even if you account for the bending of the Rutherford trajectory, that gets you to 14 Fermis. So at 30 Fermis, you're like 15 Fermis away. So that's so all you see is Coulomb. Well, the experimentalists like to say that they put a cut in the impact parameter. What they do is they in fact put a cut in the scattering angle, which can be related to the impact parameter by the Rutherford scattering formula. Now, the kinematics of this reaction is such that iconal approximation can be used because these reactions are typically done at about 50 million electron volts per nucleon or larger. And it can be understood as a direct reaction, meaning there is no compound nucleus formation. So now, there is a very strong Coulomb interaction between these two nuclei. There is this monopole term in the interaction, which is highly non-perturbative. But that can be subtracted from the Hamiltonian because the monopole interaction only determines the trajectory. It doesn't contribute to breakup. So if you are looking at breakup cross sections, that part can be subtracted from the Hamiltonian. You only keep the higher multipoles in the expansion of the charge distribution of this nucleus. Yeah.
Didn't you say that for these halo nuclei, the center of mass and the center of charge are different? So I can easily expect that it does have an impact because it pulls the charged core somehow it pulls it away more strongly than the neutron.
It pulls,
So the reduction between the charged AT core, I would say, and the left target. Whereas the peripheral
okay.
field is so strong.
I guess it would depend on what resolution you are looking at, right? If you, yeah, that's an interesting question. So you're saying that the center of charge is here, but the center of mass is somewhere here. So this interaction should happen. It should. It should act on the So yeah, I guess it depends on the resolution you're looking at. For that, that should be if you do not resolve this distances, I think it should act on the. You should see this whole blob as a charge thing. That's an interesting question. Let's discuss that later. So. Now, since this monopole term can be subtracted from the Hamiltonian, the problem becomes highly perturbative. In fact, the first order perturbation theory gives the almost exact answer. Higher order corrections have been shown to be small. Now, since this dissociation happens at large impact parameters, the virtual photons that are exchanged, they are long-lived, so they are close to the mass shell. So the cross-section for this process can be expressed in terms of the photonuclear cross-section, the photodissociation cross-section with real photons. With this function n pi, pi here is E or B, the electric or magnetic nature of the photon, and L is the multipolarity. So that could be E1, E0, B1, and so on. So these are called the virtual photon numbers introduced by Fermi. So this cross-section can be related to photodissociation cross-section, which can then be related to neutron capture cross-section by detailed balance because they are reverse processes. So we can get a lot of important information out of this Coulomb dissociation cross-section measurements. Like I said before, since the monopole term has been already subtracted, Coulomb dissociation can be understood as dipole excitation, because higher multipoles like quadrupoles and octupoles, they have been shown to be very small. For example, for lithium-11, the quadrupole term is a factor of 100,000 times smaller than the dipole term. So in the end, with all these approximations, you get this formula which is almost as good as the exact thing. So you have the Coulomb dissociation cross-section. That's the virtual photon number for E1 photons. B here is the binding energy between the neutron and the core in the bound state, the separation energy of the neutron. And E is the relative energy of the fragments after breakup. So that would be the photon energy. And that's the square of the reduced matrix element. It's called the reduced transition strength for the E1 operator. So it's just the reduced, it's just the square of the reduced matrix element of the dipole operator between an initial state, which is a bound state, and a final state in the continuum. So you see there's this nice separation between structure and reaction here. This function contains all the information about the kinematics of the reaction process, and this function depends only on the structure of the halo nucleus. This separation is not so clear in the other experiment that I showed you, the matter radius experiment. That's why it's a very clean probe of halo nuclei, this Coulomb dissociation studies.
In the experiment, are they detecting both fragments?
Even though they detect both fragments, my understanding is that they only measure the energy of the carbon-18, I think.
Okay, but
Yeah.
my question, the reason for my question is then you said that the monopole only contributes to the trajectory, but it doesn't contribute to breakup. So if somehow you have to be sure that all your events are breakup, right? And you know that if you take both of them, but maybe they have a different way of doing that.
Yeah, they detect both of them, but I think they measure the momenta and energy of just the carbon-18 fragment.
Do you have the feeling how low in your collision energy you can go for this to still be a good approximation?
Which one of these? The
Well, I mean, you're making the semi-classical approximation. Naively, my thinking is that maybe that should break down if your collision energies are too low.
I think that's certainly true. But experiments are, they design the experiments such that they can use this formula, because what they're after is this dE1 by dE.
Okay. So they actually intentionally use
Yeah.
Yeah.
Okay.
Yeah.
So it's not some hand-waving thing to explain something. No, everything relies on this.
Okay. So I'll move on to effective field theory for one-neutron halos, a brief summary of the theory and applications to carbon-19. Halo EFT is useful to calculate properties of halo nuclei in the energy regime where the relevant degrees of freedom are the halo neutron and the core. So the most general Lagrangian consistent with all the symmetries is written. The symmetries are Galilean invariance, rotational translational invariance, parity, charge conjugation, time reversal. So in principle, every term consistent with symmetries must be there. So in principle, there can be infinite number of terms. But we only work with a finite number of terms because we exploit this scale hierarchy. Square root of MB, M, the mass of the neutron, B, the neutron separation energy, square root of that, that's the binding momentum, which is an estimate of the inverse scattering length, 1/A. And that scales as the low momentum scale because the neutron separation energy for a halo nucleus is small. 1/R, R is the size of the core, scales as the high momentum scale because the core is tightly bounded. The core is small by definition of a halo nucleus. So the Lagrangian is organized as a systematic expansion in this expansion parameter. So better separation of scales will facilitate calculation because that would mean that you can reach the desired accuracy by calculating fewer diagrams if the scales are well separated. Now, the short distance physics of the core at the scale of m high is unresolved, but its impact on low energy observables is taken care of by normalization. So here's some data on carbon-19, for example. This comes from 2013 atomic mass evaluations. The spin parity of carbon-19 is 1/2 plus, and the neutron separation energy is 580 kiloelectron volts. That's the new data. Carbon-18, here's a rough estimate of the size of carbon-18 from this a to the 1/3 law. We are not going to use that for any of our calculations, so a rough estimate is good enough. That's just to estimate the expansion parameter in the beginning. We are, in fact, going to revise the expansion parameter once we find out the effective range parameters. So that's just a rough estimate. The spin parity, the ground state spin parity of carbon-18 is 0 plus. And its first excitation energy is 162 million electron volts. Now that is related to your question out there. So if you translate that to a momentum scale, that corresponds to m high. That scales as m high, which means that we do not have to include this field explicitly in our Lagrangian. If that had scaled as m low, we would have to include this additional core field into our Lagrangian. So for the moment, we only have this ground state core field and the neutron. So that's the size of the expansion parameter in this theory for carbon-19. So here's the Lagrangian written in terms of the neutron and the core fields. Their masses m and m. D is the auxiliary field that represents the bound state, the halo. Delta is called the residual mass. G is the coupling between these three fields. If you ignore these kinetic terms, that would be the leading order Lagrangian with just zero range interactions. But adding those kinetic terms makes this d-field dynamic. It gives finite range to this interaction between the neutron and the core. Eta is plus or minus 1, whichever makes the effective range positive. So the propagator for this D field, the bound state, is dressed by the neutron core self-energy bubbles, which have to be renormalized. That can be done by calculating the T matrix because that can be calculated because this is just the Lippmann-Schwinger equation once you attach the external legs to this equation. So the T matrix calculated here can be compared to the second order effective range T amplitude, and the renormalized coupling G and the renormalized delta can be related to the effective range parameters by matching the position of the pole and the residue of the pole. So kappa here is the scale of the power divergence subtraction scheme, which is convenient for these systems with for this weakly bound systems. You can just ignore that because you can set kappa to 0. That would be modified minimal subtraction. That doesn't change our results in any way. So now we assume that all the higher effective range parameters are natural. Now we don't have any experimental data to back that up, but that seems to be the natural assumption because you need additional fine-tuning to enhance these higher effective range parameters. And in fact, that's a testable assumption because if this assumption doesn't hold, our EFT will not converge in the expected manner. The first shape parameter only enters at N3 LO, so we decide to stay at N2 LO where you have only these parameters. You can think of it as in terms of A and R0 or the original couplings in the Lagrangian, G and delta. So now electromagnetic interactions are introduced into the Lagrangian by minimal substitution. So that diagram is the most important diagram for Coulomb dissociation cross-section. And that carries -1 power of our expansion parameter. Because we are looking at E1 dissociation, this is a vector A photon that carries a power, that vertex carries 1 power of momentum. So did you have a question? Okay.
I didn't have a question.
Sorry. Sorry. So that diagram carries -1 power of the expansion parameter. Final state interactions are present, but they are all suppressed. This is the most important of the final state interaction diagram. And that only enters at N3LO because that carries 2 powers of the expansion parameter, because this vertex has to be a p-wave vertex now.
Is this to the power of 2 or to the power of -2?
This one is to the power of 2. So that's minus.
To the power of -2, you get 0.5.
You get suppressed by, that's 3 orders higher compared to that one, right? So you get suppressed by 0.5 to the power of 3. Since this is an effective theory, minimal substitution is not enough. You also need to add to your Lagrangian all contact terms that are consistent with the symmetries of the theory and gauge invariance. The most important of these only enters at N5LO because it carries 4 powers of the expansion parameter. Now, since we already decided that we are stopping at N2LO, we only need to calculate that diagram. These enter only at higher order.
Can I ask a question?
Yeah.
Just naive.
Okay, sure.
Does it mean that you basically work with like 10%? You expect from your result to be 10%?
All right.
Okay. So, or something else would come into play, such that it would either make the inaccuracy large or small. That's the estimate that we begin with in the beginning. I'm going to tell you later that once we determine the effective range parameters, once we fit the effective range parameters, we are going to revise our estimate, because R0 over A would be a better estimate than this naive estimate based on this hand-wavy calculation of the size of the core. So it's going to be a little better than that, but roughly it's, as you said, that's the level that we are working at. Yeah.
Probably you're going to say that, but when you say N2LO, do you include range corrections fully perturbatively, or do you use some resummation?
No, we do not. No. Our N2, so when we say N2LO, we do not include the range corrections fully perturbatively. That's all we do. So we just look at the effective range expansion and see where the next step parameter enters.
Okay, so this is exactly the propagator. If you're using it, you're not re-expanding.
No, we are not. Yeah.
Can you go back to your expansion parameter where you said?
Yeah.
So here you say that your initial guess is 2.7 Fermi from this 1.28 to 1/3 law.
Yeah.
If you would convert the 1.62 MV into a value for big R, is that of the same order?
Yeah, that's almost the same value actually. So that's the only diagram we need to calculate up to N2LO. So once you calculate the matrix element and isolate the projection dependence, Wigner-Carr theorem, we get reduced matrix element. This is the square of this reduced matrix element. Mu is the reduced mass. Z is the charge on the core. M is the mass of the core. Gamma 0 here is the binding momentum, effective range. P is the relative momentum in the final state. Relative momentum between the fragments. At this order, the binding momentum gamma 0 is the real and positive root of this equation. So it's related to the effective range parameters. The asymptotic normalization coefficient of the halo neutron is again related to these parameters. So you can think of it as it's a 2-parameter problem, whichever way you look at it. Some people like to think of it as effective range parameters A and R0. In the nuclear physics community, they like the neutron separation energy and the asymptotic normalization coefficient. And 4 parameters, 2 equations connecting them. So if the values of these parameters were available, we could have made a prediction for the Coulomb dissociation cross-section and compared to the experiments. Now, although the neutron separation energy of carbon-19 has been well known, it had been well known by the time we did this calculation, the asymptotic normalization coefficient of the halo neutron was not known. So what we decided to do was to do a 2-parameter fit to determine both of these quantities. So essentially we are using the Coulomb dissociation data as input to find out the neutron separation energy and to fit the neutron separation energy and the ANC.
So that's the data, that's the angular distribution of the cross-section, and that's the energy spectrum. So we do a 2-parameter fit to the data. The dashed line is fit to data shown in the same figure, and the solid line is the fit to the combined data set. We minimize the total chi-square. So in this graph, we only fit to the first 6 data points, because at high energies, the AFT does not converge anymore. That would be beyond the breakdown of our AFT. So we fit only to the first 6 data points, but you can see that the agreement extends much further than the region of our fit. And these are the extracted values, the scattering length, effective range, and this correspond to a neutron separation energy of 575 kiloelectron volts, which agrees with the value of 580 keV that I showed you earlier, which is partly based on the same experiment. They look at this experiment in the recent atomic mass evaluations. They look at this experiment, and they look at one other experiment by Madalena et al., the momentum distribution experiment. And then that's where the value in the atomic mass evaluations comes from, and we agree with them. So for reference, I showed you earlier a value of 530 keV deduced using a Wood-Saxton potential from the same experiment. So we think that we did a better job, because we have an error, because they worked in the potential model. They cannot have any theoretical error bars. We have a theoretical error on top of the statistical error.
What all does this EFT error include? I mean, you mentioned the mass
Yeah.
ratio, but
Yeah, that's the EFT error.
okay. So it doesn't include the effects of assuming that you can neglect the higher shape parameters?
That's actually, that goes with the power counting. Actually, those two are related. What this doesn't include is all the approximations that you make in the reaction theory that I told you about, like higher order Coulomb corrections, right? Using iconal approximation and direct reaction theory, all these higher multiples, those ones, they have to be assessed separately. So this doesn't include the errors in the reaction theory. But that's a good question. I should have mentioned that.
But they should be in these data points, right? Because would be
Yeah.
or you're fitting to the raw data, so you're not fitting to dB by dE.
No, this is the cross section. Yeah.
What is these two different lines, the solid line and the dashed line?
So the dashed line are fit to the data shown in the same plot. The solid line is obtained by minimizing the total chi-square. So it's fit to both data set.
But the effective range you get is pretty much what your simple estimate was in the beginning, right?
Yeah. Yeah, so now if you take this ratio between R0 and A, that comes to a value of 0.33, which is better than the initial guess of 0.5 that we started with. So that's the value we use to estimate these EFT errors.
But the reason you got the 0.5 then it was not that R not changed. The reason was that instead of A you used the separation energy, right? That made a difference.
Yeah.
And that.
Yeah.
So if you're conservative.
Yeah.
I mean, you still have, since R naught is the same value still, and the separation energy that you get is consistent with the one you started in the beginning.
Yeah.
If you're a conservative person, you would say still say your expansion parameter is between 1/3 and 1/2.
Okay. Yeah.
I mean, your calculation, of course, your calculation when you carry it out in the end, it works very well, right? So probably it's closer to the other parameter, but I think from the red numbers here, it could still be larger. I mean, you have a range.
Yeah. Yeah. So.
But important at this stage because the statistical error is larger.
Yeah. Yeah. So once these parameters are fit, the longitudinal momentum distribution of the cross section is now a prediction. Now that's our prediction. So it turns out that the width is sensitive to the neutron separation energy. Like I said before, small separation energy means spread out wave function, coordinate space, sharper peak, and the asymptotic normalization coefficient only enters the height. Now, unfortunately, we could not test our prediction for A and C because data with normalization is not available for a high Z target. I should have said that this is for z equal to 1. So you would have to scale that up by z square for where z is the charge of the target, atomic number of the target. So so the only data that's available for a high z target, tantalum in this case, NaCl experiment, measures their peak in arbitrary units. So we cannot test our prediction for the ANC. But what we could do is fit our height to the data and then compare the widths. Also, everyone who's looked at this data has had this problem that Lorentz transformation doesn't get you from there to there. We think that's because of they say that they have 1 or 2% error in the absolute energy calibration that seems to be consistent with the discrepancy that we are getting. So there are newer experiments with low Z target where the experimentalists, they express their results in the rest frame of the center of mass of the fragments. That would be more convenient for comparison. But for the moment, we have to work with the data that's available, which means that we have to fit the height and also the position of the peak, and the width is the only prediction. And I think that's a good agreement. So moving on to two-neutron halos and applications to carbon-22. That's the Schrodinger equation for the three-body bound state bound by pairwise interactions. V1, for example, is the interaction between second and third particles. Once you define the Fediev spectator functions like this, they satisfy this modified STM equations. And for two-neutron halos, you have two identical particles and a third particle, so you get a set of two coupled integral equations for the spectator core function and the spectator neutron function. All the two-body propagators shown here are dressed, so they are renormalized by, at leading order, they can be renormalized by using the two-body scattering lens as input. However, a three-body contact interaction enters at leading order. So it's impossible to make prediction without having at least one three-body datum as input. So once you include that three-body contact interaction, this coupled integral equations can be solved for these spectator functions, and from that you can calculate the wave function, the three-body wave function in terms of this Jacobi momenta P and Q. P is the relative momentum between the pair, and Q is the relative momentum between the spectator pair system. So from these wave functions, you can calculate the form factors like this two-body form factor. The slope at low k square gives you the mean square distance. For example, if this is the Jacobi representation with the core as the spectator, that would be the distance between the two neutrons, the mean square distance between the two neutrons. And if that's the Jacobi momenta with the neutron spectator representation, that would be the distance between the neutron and core. And these are calculations by Canham and Hammer for carbon-20. And these are the form factors plotted versus k square for the neutron core system and for the neutron-neutron system. So they also used this wave function to study the possibility of finding excited Efimov states in different two-neutron halo nuclei. So here they plotted the square root of the neutron-neutron energy. I apologize if this is not too clear. So they plotted the square root of the neutron-neutron energy expressed in the units of the three-body binding energy on this axis, and the square root of the neutron core energy expressed in the units of the three-body binding energy in the vertical axis. Positive neutron-neutron energies corresponding to bound neutron-neutron systems in this right half plane. That would be unphysical for nuclear physics because we know the neutron-neutron system is unbound, but that could be relevant for atomic and other systems because we know that this should be universal at this order. So again, unbound neutron core system on this side and bound neutron core systems on the upper half plane. So all nuclei lie outside this region included by these boundary curves. This included region is where you need to be to have at least one bound excited Efimov state above this ground state. And A here is the mass number of the core. So it looks like carbon-20, yeah.
What will be the ratio of Efimov
For this,
What will be the ratio between energies for this mass ratio, like 1 to
it would be like 17 or 18, I guess, right? Something like that.
I can look it up and tell you the talk.
Yeah. So instead of 22.7, it should be a little lower. I think for this range, carbon 20, for example, if I remember correctly, that would be like 17-ish.
Sounds too large, but okay.
Maybe we'll need to.
Just to make
Yeah.
sure I understand, so you have two neutrons, right?
Yeah.
Which I can think of as two identical fermions.
Yeah.
And then you have your core.
But
Yeah.
you have their distinguishable fermions because they have opposite spins. So there is
Oh, because
distinguishable
of the-
particles.
Yeah.
Oh, so it's
There's
three.
three.
So it's, okay, so it's
yeah.
basically three distinguishable particles.
Right.
With a large mass
Yeah.
ratio.
Yeah. Yeah.
Okay, so
Yeah.
in the zero range limit, if the scattering names,
Yeah.
if two of the scattering names were large, you
Yeah.
would actually have
Yeah.
average states for any mass ratio. Is that correct?
I think so, yes,
Okay.
with a large factor. And
Yeah.
so here, I mean, you even have 3 large scattering lengths, just
Mhm.
they're not all the same.
Yeah.
Um,
Okay, thanks. That helps that these are distinguishable, so that's
Yeah. So I should have clarified that the formalism that I showed you, this sign and everything, it works out because we know that the neutrons have to be in spin singlet because I'm working with 0 plus two-neutron halos with 0 plus core. So once the neutrons are in spin singlet, the antisymmetrization of the wave function is taken care of by the spin part. So the wave function, the space wave function, is completely symmetric. Not completely symmetric, but symmetric with respect to these two neutrons.
So you can basically have
Yeah.
no node
Yeah.
manifestation.
Yeah. Yeah. So you had a question?
Did these things include any range corrections, or is it all leading order?
This is leading order, but here's the leading order EFT error band. So you would expect the range corrections to be within this band.
Why is it so narrow for this one? It looks narrow, at least on the plot for
For a leading order?
I mean, it's a relative plot, right?
Oh,
That's what it
yeah,
means.
you
Yeah.
can scale that.
Yeah. So here it looks like carbon 22 because of the large experimental uncertainty could lie inside. But the value of ENC that was used in this analysis came from 2003 atomic mass evaluations, which was later revised in 2013 to the value that I showed you earlier. So the value used here is 162 keV. That's the older value. The newer value in 2013 is 580 keV, which would put that point way up there. So we did similar analysis like in Canham's paper. So we first worked in the point core limit where we treat the core as a point particle. So we do not include the finite size of the core in our calculation of the RMS matter radii. So that's what this means. This subscript means. That's the mean square radius of the halo nucleus in the point core limit. B is the two-neutron separation energy now. It's the three-body binding energy. And M is the mass of the neutron. So the ansatz here is that because this is a dimensionless thing, it should be a function of dimensionless ratios only. At a given A, you have three energies, the neutron-neutron energy, neutron core energy, and B. But the ansatz is that it should be a function of only two variables. And that's indeed the case. That shows how it depends on these two dimensionless ratios. It's a 3D plot calculated at A equal to 20. Now, in the unitary limit, if the two-body energies are 0, this function should only be a function of A. So this should be a truly universal curve. Given any systems with two equal masses and one unequal mass, you should get this scaling between the binding energy and the RMS matter radius for this point-like heavy mass. So actually, when A is very large, even that's there is totally no scale in the problem left. So the mean square radius should scale as 1 over the three-body binding in the unitary limit.
So here you took, since there are different matter radii for a three-body system, you can define this for one particular
This
one?
is the RMS matter radius, and it I guess it can be only be defined in one way. This is just the so it's not so if that's the core, that's the neutron. So it's not the distances between the particles or anything. It's just the RMS matter radius measured from the center of mass. It's just this thing. The density, let's say, r square d cube r. That's the total mass density. That could be.
Okay, but how you are calculating this via that formula? I mean,
And
what it
actually,
comes out
it
with
can.
would be like
Okay,
a linear
okay.
combination
So
of
let me.
the
Yeah,
radii
right.
and the
Yeah,
Coulomb moment.
right. Okay, let me try to explain what we did. So we treat the neutrons as point particles, and let's say that's the three-body center of mass. So here's the formula for the mean square radius. So it should be, let's say, m times this distance, r1, let's say, square, plus r2 square, plus, I'll also multiply by the total mass here. So that should be equal to that, plus this m times, if that is r1, r2, that's r3, r3 square. That accounts for this thing. So what we actually do is, okay, if that was, so for this case, for the point core limit, that's all we do. So this can be related to the Jacobi coordinates. It's easy to relate. For example, this r3 would be 2 over a is the mass number of the core. So 2 over a plus 2 times this r, c, and n. That would be this distance r3. So so actually, yeah, that's a good point. I should have said that. These are the distances that we get in Jacobi coordinates from our form factors, and they have to be related to these distances, and then we can calculate the mean square matter radius by this simple geometrical argument.
That looks just like the hyperradius, basically, what you call
Okay.
the,
Yeah.
R square.
Yeah.
That's the standard definition, right? That's
Yeah.
and to account for the finite extension of the core, we have to replace this by an integral. For example, if you have R3 and you could have this, to account for this distribution, you'd have to convert that to an integral. So you have this thing as a function of capital R measured from the center of mass, and then you have R3 plus vector R square. So that's how you'd account the finite size of the core into account.
But you don't do it here.
So in this slide, no. We do it later. Yeah.
Yeah, so it's like, so you're saying that when all the scattering lenses are infinite,
Yeah.
then you basically your binding energy is inversely proportional to 1 over r squared.
Yeah.
Okay.
Which is obvious on hindsight because there's no other scale left in the problem.
Is it like kind of log behavior, or is it?
So all I can say is that this becomes flat as expected for large A, because once A becomes large, it should depend weakly on A. So other than that, I haven't tried to look at the what function would best fit this curve. Yeah.
Another question: how are these two-neutron halos studied experimentally? So you have to somehow subsequently remove first one neutron, then the other, or do you break it up into 3 particles?
For Borromean systems, you can only break up two neutrons at the same time. So this, yeah. So this one is for a Borromean system, yeah. So.
Now, what do they do in the experiment? Do they break it up in some, like the same kind of thing they did for the one neutron halos that you showed in the beginning, or what do they actually measure?
For two-neutron halos, I think the experiments that have been done yet is on lithium-11, which is boron. They just did some some experiments with carbon-22. They are analyzing the data right now. The results aren't out yet. So I don't know of any experiment in which they did a non-Borromean two-neutron halo dissociation. I should look that up. There are two possible channels, as you said. You could have a three-body final state, or you could have a two-body final state with a bound neutron core subsystem going out. I think they should have both, right? In the yeah.
And they measure same kind of thing. Measure
Yeah.
acceleration energies.
Yeah. So in 2010, this paper came out. They measured a large reaction cross section for carbon-22, and they deduced a very large value for the RMS matter radius of carbon-22. That's the value, 5.4 Fermis, which is it breaks all records. It's much larger than anything ever seen before. So so here's a summary of experimental data on carbon-20, 21, and 22. Carbon-21 is known to be unbound. The ground state spin parity of carbon-20 is 0 plus, and that of carbon-22 is 0 plus. Carbon-21 is 1/2 plus. So what this means is that carbon-22 can be thought of as a Borromean two-neutron halo with all two-body subsystems in S-wave. Now, actually, you can have D-wave two-body subsystems. It's possible to add the angular momenta in such a way that you get 0 plus in the end. But our answer is that the configuration mixing of this D-wave should be small, because D-wave has this angular momentum barrier which has a confining effect on the wave function. So that would be very difficult to get this large matter radius even with very, very, very small energies if there was a significant mixing of the D-wave configuration. Actually, we in fact did some calculations to show that the effect of this D-wave configuration mixing should show up only at higher order. So at least to the order to which we are calculating, which is leading order, it's just purely S-wave. So these are the energies. That's the 1 neutron separation energy of carbon-20, 2.9 MeV. So the carbon-22 2 neutron separation energies, they are not very well measured. You can see the large uncertainties. It's like 3 times the size of the value itself. And that's
These S2N values, are these are measurements?
Yeah, these are measurements. That I believe is mass measurements. I believe that both of these are mass measurements. Yeah.
Why is the sign different?
Okay. They found a value that's consistent with unbound carbon-22. But because of the error bar, it's also consistent with the bound carbon-22. So that's...
But the other one's also consistent with the number, right? So if you look at the 94...
Yeah, that one is also consistent with unbound carbon-22. So
Are you absolutely sure that these are measurements? I mean, it could be that I thought both Suzuki and
okay.
yeah.
Yeah.
I mean, of course.
Yeah. So that one is... So I'm sure that this one is mass measurements. I'm not absolutely sure that comes from mass measurements. I think, I don't know. I'll have to look that up.
You could put some combined
Yeah.
analysis.
Yeah.
So,
Yeah.
I didn't follow. How does the D-wave, the possibility of a D-wave lead to confinement of the wave function?
Because okay. So angular momentum barrier in the radial Schrodinger equation, let's say for a two-body system, looks like this with factors of S cross square over M and so on, right? So if you it's repulsive. So it's a 1 over R square potential. So let me draw it on that side. If you put it on top of attractive potential, let's say any attractive potential, if you add those two, you get a barrier here. If you put a short range, if you add a short range attractive potential to this 1 over R square potential, you get this kind of a shape. It goes as 1 over R square at large distances, but you get a bump here, right?
Go back
So,
up again.
it,
Near the origin.
near the origin, it would go back up if, well, yeah. So it depends on which one is stronger, right? So if this falls off slower than 1 over, if this rises slower than 1 over r squared, then that would go back up.
It should, because otherwise you get singular.
You get particles falling to the center. So this is what I wanted to focus on. Like so the wave function has to penetrate through this angular momentum barrier, and that confines the wave function. It leads to wave functions with a smaller tail. So once the wave function has a smaller tail, if you calculate the sizes, for example, r square psi, the mean square radius, if the wave function falls off at large distances, this integral contributes at low r only. Some, let's say, r naught. That's, yeah. So that's the data. I think I'm running out of time.
Could you explain once more? So
Yeah.
It's like, if I understand correctly, so if the separation energy is like negative, then
Yeah.
it kind of splits immediately.
Yeah.
Basically, don't see
Yeah.
any switch,
Yeah.
right?
Yeah.
So I would say that it's like
Well, this analysis is under the assumption that the separation energy is positive, and if it's negative, then this state is like a resonance, and then sort of this analysis would not apply.
So,
but what I'm trying to is like in experiments they have to see immediate changes because I mean the time scale when the nuclear with the separation energy of neutron is negative is actually like it's of the of like nuclear time. It's just immediate decay.
yeah.
And if it's actually bound, even EB, then it should go through some weak channel, and it can, of course, be a really short time, but it's like it's measurable. So I would say that it's like if it's bound and unbound, it's supposed to be measurable, like immediately. Like it is a sign of the science.
I made the same argument to an experimentalist once. I said, why can't you just you know that it's bound, so why can't you just just code this value? Why don't you just say that it should go from 0 to say 32? And then he said, no, we can't do that. We cannot make any assumption that.
Actually, know it's.
You know it's bound, so why don't you use that information? That's
basically it means that it's bound not only because of the neutrons. It's like it bounds as a whole. Then if you like, if the separation energy is if the separation is positive, but it's still kind of bound, then it means that it's bound as a whole. You cannot just.
But the two-neutron, if the two-neutron separation energy is negative, then it cannot be bound as a whole, right?
No. It can be. It can be bound as a whole.
no, because the
whole.
n subsystem is unbound.
No. Then it's
No, if it's negative, then it's not bound.
It's
right?
negative.
Then it always splits off the neutrons.
Are there lifetime measurements for that thing? So maybe when we say
Ah,
bound, do we really mean it lives an infinitely long time, or do we say it just
When we say bound, we mean it does not decay via the strong interaction.
Yeah.
So that's
there are
Yeah.
lifetime measurements
Right.
that do
Yeah.
include that? That's my
Yeah.
This
The-
is a very, this is a very well-known, difficult problem to
Yeah.
determine whether
Yeah.
you have a deeply bound state or not.
Yeah.
I mean, it's the same thing in atomic physics.
Yeah.
The number of two-body bound states in a van der Waals potential. I mean, that's a very, very tricky question whether that last state is bound. You don't have direct access to the sign of the scattering rings when, especially when the scattering rings is large. From the cross section, you don't get glass measurements either. This is, I think it's very much the same thing.
No, that's true. It depends how they measure. Because what I would say is that if you can
Okay, sorry.
so it's like nuclear physics, I might.
Okay. So
carbon 21.
yeah,
It is unbound. It is a resonance state, or
it's a virtual state, right?
virtual
State, yeah. So the difference is where you have the poles in the scattering matrix and the complex energy plane or the momentum plane. So here are the scales. 2-neutron separation energy of carbon-22. We treat that as a low scale. That of the carbon-20, that's a high scale. The size of carbon-20, that scales as m high. So the neutron core energy is unknown. The carbon-21 virtual state energy is unknown, but we treat it as low scale and treat it as a free parameter. We do not use any of this data because these are not very well known. So that again is a free parameter.
So with carbon-21, you have the same problem, right? There are experiments that haven't seen this as a state, so people believe that carbon-21 is not bound. But if you take, so he has taken the 1-neutron separation energy for carbon-20, you take from this NNDC database. So this is not real experimental data, it's evaluated experimental data where they put in some model. And this NNDC database also gives a value for ENC. And if you believe that value for ENC, then carbon-21 would be bound.
They're not consistent.
But experimentalists haven't seen it, and they would tell you it's not bound. So I mean, the situation on these input parameters is not really clear cut, right?
Yeah, there are different experiments that give different results. So it's not easy. It's not well defined what to use as input parameters. We use the wave function that I showed you for a Borromean 2-neutron halo to constrain these parameters, neutron core energy and the 3-body binding energy, using the experimental datum on the matter radius of carbon-22. So this blue line is where you need to be to produce this central experimental value of 5.4 Fermis. The green line corresponds to experimental value, the plus 1 sigma, which is 4.5 MeV, 4.5 Fermi, and that would be plus 1 sigma. That's 6.3 MeV, 6.3 Fermi. And the bands here are the FT error bands. So even when you consider the 1 sigma experimental uncertainty and the leading order FT error bands into account, you can constrain these two parameters in this region. Now it's the same plot shown in logarithmic units. Here, the purple region is where you need to be to have bound excited Efimov states, and these two do not overlap, at least in the plotted region. If we look at low enough neutron core energy, which is numerically difficult, these two regions should overlap, because at that point, there are 3 two-body subsystems, and 2 of them are resonant when ENC is low. So it should have bound excited Efimov states there. So these two, we would expect them to overlap at somewhere down there. But for carbon-22 to have bound excited Efimov states, carbon-21 needs to be tuned very close to the threshold. So it should have a very low-lying virtual state. But in a subsequent analysis by Mosby et al., they did not find any low-lying virtual state or a weakly bound state in carbon-21. They constrained the scattering length of carbon-20 neutron to a value less than 2.8 Fermis, which translates to more than 1,000 keV. So it looks like carbon-22 cannot have excited Efimov states, but that's based on the assumption that this value will hold up.
Back to your plot, the way you've chosen the sign for ENC here says that if ENC is positive, then it's not bound, right?
Yeah, it's unbound, yeah, right. So there's a more recent paper on calcium-62 using interactions from chiral EFT and couple cluster theory and halo EFT by Gota Hagen and others, and they see some promising signs of finding Efimov states in calcium-62, which I think is within the range of FRIB, so that should be interesting. So moving on to Coulomb dissociation. How much time do I have? So this should take like 5 minutes.
That's fine.
Sorry. So moving on to Coulomb dissociation of carbon-22. So here's the dipole operator for a 2-neutron halo. So that's the amplitude for Coulomb dissociation in the plane wave impulse approximation, where the initial state is the 3-body bound state, the dipole operator, and the final state is free state in terms of the Jacobi momenta Lm is the angular momentum in this of the pairs, and lambda mu of the spectator pair system. So that's the matrix element. Once you factor out the projection dependence, you get reduced matrix element, and these are the squares of the reduced matrix element, dB1 over dE. And that shows the sensitivity to the three-body binding at different neutron core energy, and that shows the sensitivity to neutron core energy at the same three-body binding. So, so this is in the plane wave impulse approximation. There's actually a very tight constraint on the area under this curve, which comes from completeness of this final states. It's called the non-energy weighted sum rule, and I've checked that the non-energy weighted sum rules are satisfied for all these curves up to 1 to 2%. Maybe I can increase the accuracy of my code later, but I'm not focusing on that right now. So at present, I'm satisfied with how well I can satisfy the sum rule with this. So now we saw in the two-body sector in carbon-19, for example, that final state interactions were suppressed. Here, the situation is different because angular momentum addition only demands that either L or lambda is 1. So L is this pairwise angular momentum. So it's possible that L can be 0, but lambda can be 1. So you can have final states in which all two-body subsystems, two-body interactions are in the S-wave channel. And since we are dealing with systems with large S-wave scattering lengths, all these interactions need to be accounted for even at leading order. So the final state wave function has to be constructed with all S-wave two-body interactions included, which means that the final state wave function will no longer be a free state, but it has to be constructed like this, where T is the two-body T matrix, the S-wave T matrix, and these F's are the Fediev spectator functions that have to be calculated above the three-body breakup threshold now. It's there's this problem, well-known problem of moving singularities associated with that, which Sebastian would argue is logarithmic singularity, so it's integrable. But I'm using this Hetherington-Schick method by analytically continuing to complex momentum to avoid the singularities. So that's work in progress, and we expect the result very soon. So the conclusions. We determined or fitted the neutron separation energy of carbon-19 and its asymptotic normalization coefficient using Coulomb dissociation data. The neutron separation energy agrees with the momentum distribution data, but the asymptotic normalization is yet to be tested. The 1 sigma experimental error on matter radius imposes upper bound of 100 keV on the 2 neutron separation energy. This is a much stricter constraint than other studies that use the same data. Absence of low-lying virtual states in carbon-21 rules out the possibility of finding excited FMO states in carbon-22. And there is forthcoming data on carbon-22 that's expected to provide better constraints on its 2 neutron separation energy and on the carbon-21 virtual state energy. Thank you.
Thank you very much. Questions? Or
I have one.
So should it stop?